Welcome to introduction to IoT uh, MOOCs course. Today we are going to cover introduction to IoT quadrant one. In this quadrant, we are going to get introduced to the different fundamental concepts behind IoT and the basic technologies, connectivity devices that are required, and an overall understanding about how IoTs are made. So we are going to have in this lecture an understanding about all of these concepts. But first, let us get motivated about why IoT is required. So it has been anticipated that very soon all the different things that are going that we are seeing around us and that we have around us are going to be internet work. They're all going to be interconnected. So at present, what we enjoy as services as internet-based services is basically a connection of different computers and computing devices. So basically, this capital I internet that all of us use is basically a global network or an internet work of different computers and computing devices. Now, what Internet of Things says is that the scope of this internet is going to be expanded. So it is going to be expanded beyond computing and computing devices being connected. It is going to interconnect different things that physical objects that we see around us. The different objects such as the lighting system in a room, the lights, the fans, the air conditioners, and anything and everything, including things such as the toothbrush, the microwave oven, the refrigerator, and so on and so forth. And not only in our homes, but also in our businesses, such as internet working, different machines, internet working, different equipments, and so on. So each and everything that we see around us that we use at our home, in businesses, in workplaces, everything being internet work. So this is the whole vision of internet work of things, internet of things. Now there are several challenges that are going to arise if we want to do it. But before, let us also discuss about why it is going to be required, why internet of things has become so popular, why it is going to be required. The reason is that IoT is envisaged to be able to provide advanced level of service to the society, to the business, and so on. So advanced levels of services can be offered with the help of IoT based technology. So what is going to happen is these different things, the chairs, the tables, these lighting system, the watch or anything and everything that you can think of, all of these are going to be fitted with embedded systems, embedded electronics, and information technology. So that they have some basic computing platform in them, attached to them, and then they are going to be acting as different nodes of that particular internet, the internet of things, right? So what is going to happen is these systems, these things are going to be all equipped with embedded systems, and these embedded systems along with embedded electronics, embedded processor, embedded communication systems, and so on. So they are going to help in connecting different other things that are around them, and depending on the application requirements, depending on the specific goals of the business, and then a big internet is going to be formed, which is much bigger than the current internet of computers, and that is the internet work, internet of things. Now IoT is one of the building blocks that is considered to be of use for developing smart homes and smart cities. So at present, not only in our country but throughout the world, there is a lot of interest on developing smart cities and smart homes. So IoT is one of the enabling technologies to make the city smart, to make the home smart. So how it is going to be done, that is going to be more evident as we proceed through the different lectures and the different intricacies that are going to be there in building this complex internet of things is going to be evident through different lectures that we are going to go through in this particular course. So IoT architectural overview. The Internet of Things hasn't been around for very long. However, there have been visions of machines communicating with one another since the early 1800s. Machines have been providing direct communications since the telegraph. The first landline was developed in the 1830s and 1840s. Described as wireless telegraphy, the first radio voice transmission took place on June 3rd, 1900, providing another necessary component for developing the Internet of Things. The development of computers began in the 1950s. The Internet itself, a significant component of the IoT, started out as part of DARPA, Defense Advanced Research Projects Agency, in 1962, and evolved into ARPANET in 1969. In the 1980s, commercial service providers began supporting public use of ARPANET, allowing it to evolve into our modern internet. Global positioning satellite GPS became a reality in early 1993, with the Department of Defense providing a stable, highly functional system of 24 satellites. This was quickly followed by privately owned commercial satellites being placed in orbit. Satellites and landlines provide basic communications for much of the IoT. The Internet of Things describes a vision in which everyday objects are connected to the internet, be identified and communicate with other devices. These objects are typically referred to as smart objects. The aim is to digitizing applications and process to make them easier and more efficient. Smart objects, also known as intelligent objects, are objects that are equipped with the positioning and communication technologies and are integrated into a communication network, the so-called Internet of Things. These intelligent objects can enter, store, and process data and interact with other objects, systems, or people. They can be embedded or fixed in other objects and capture data about position and sensors, as well as execute decision and control functions. The Internet of Things is a computing concept that describes a scenario where everyday physical objects are connected to the internet and can design and can identify themselves to other devices or processes via an address. The IoT is significant because an object that can represent itself digitally becomes something greater than the object by itself. No longer does the object just relate to the process, now connects to surrounding objects and database data, permitting big data analytics and insights. In particular, things might communicate autonomously with other things and other devices, such as sensors in manufacturing environments or an activity tracker with a smartphone. IoT has evolved from the convergence of wireless technologies, microelectromechanical system, microservices, and the internet. There is not such a unique or standard consensus on the Internet of Things architecture which is universally defined. The IoT architecture differs from their functional area and their solutions. However, the IoT architecture technology mainly consists of four major components. Components of IoT architecture: sensors, devices, gateways and networks, cloud management service layer, application layer. In this four-stage IoT architecture, we have four layers: sensing layer, network layer, data processing layer, application layer. Sensing layer gathers data, network layer transmits data to data processing layer for processing purpose. After processing the data, it is sent to application layer for user access. This is the IoT World Forum IoT reference model. And what are the IoT design principles and needed capabilities? Design for connected devices for IoT applications, services, and business process considers the ease in designing the device's physical data link adaptation and gateway layer. It means availability of SDKs, prototype development boards with smart sensors, actuators, controllers, and IoT devices which are low in cost, and hardware which embeds and are preferably open source software components and protocols. Hardware which includes the device should embed minimum number of components and use ready solutions for ease in designing local devices, personal area, network, and security connectivity with the internet. Designing also considers ease as well as affordances. For example, RFID or code. The card has an embedded microcontroller memory, OS, NFC, peripheral interfaces, access point based device activation, RF module, and transceiver at low cost. A wireless sensor uses, for example, a mobile terminal mode, which is a low cost device with an open source OS and software components. Usages of modes provide ease and affordance in a wireless sensor network. Devices of smart homes and cities use Zigbee, IP, or Bluetooth LE 4.2 due to their affordability, ease of designing, usage, and low cost. And these are modern day IoT applications. Modern day IoT applications are healthcare, uh, pollution monitoring, transportation. Almost IoT occupies all the sectors because nowadays all the things are going to be connected to IoT. So in the modern day IoT, people are talking about different applications such as smart parking, such as the health monitoring, noise urban maps. That means noise maps in a particular city or an urban environment, smartphone detection, traffic condition, smart lighting systems, waste management, smart roads, river flood monitoring, smart grid tank monitoring, water tanks, etc. Tank level monitoring, photovoltaic installations, water flow monitoring, stock calculations, access control, presence of different liquids, hazardous materials, and so on and so forth. Large number of applications envisaged. In fact, there are many IoT oriented systems have been built already. They have been prototyped. Some have been much more advanced than a simple prototype, and these can be used for serving not only these applications that I just mentioned, but also a large number of different other types of applications. For example, healthcare, special applications, and so on and so forth. The number is many, and anywhere that you see there is a problem, IoT is quite likely can be used in order to improve the efficiency of the solution to that particular problem. Different other applications such as forest fire detection, snow level monitoring, landslide monitoring, and avalanche prevention. Actually, landslide monitoring in our country. There have been different institutions that have already developed systems for landslide monitoring. So without getting into the details of it, let me proceed further. So we have earthquake early detection and monitoring seismic system. Seismic sensors have been developed. They can be connected. They can be internet over and so on. Water leakage monitoring in a water delivery system, water transmission system in a city, radiation level monitoring, explosive exclusive monitoring and hazardous gas monitoring, supply chain control, NFC payment, intelligent shopping applications, and smart production management. As I was telling you before, you can in fact think of IoT applications in almost any sphere of the society, any sphere of life. So, what is expected in order to build IoT is to have trillions of sensors, billions of smart systems, millions of applications, all of which are going to be internetwork. They are going to be made synchronously operated in order to build IoT. Actually, in terms of the baseline technologies, there are quite a few baseline technologies that can be used. Machine to machine communication is one. In machine to machine communication, one machine directly interacts with another machine, directly interacts with another machine. One machine directly talks to another machine, communicates with another machine without any human intervention. We have the cyber physical systems where the physical systems are basically equipped with computer and connectivity, computational and connectivity mechanisms. So IoT and machine to machine, these goes almost hand in hand, but there is a distinction. Whereas M2M is just concerned about communication and interaction between two machines or two devices using technologies such as cloud, regular internet, and so on. In the case of IoT, the scope is much bigger. In IoT, we are talking about not only machine to machine communication, but different other things as well. So M2M can be construed to be a part of IoT, while M2M standards have a prominent place in the IoT standard landscape. However, IoT has a broad scope than M2M, so there can be broader range of interactions and not simply machine to machine interaction. There can be interactions between not only machines and machines, things and things, but also things and people, things and applications, and people with applications. IoT and Web of Things, Internet of Things are often confused to be one and the same, but there is a distinction. The Web of Things basically focuses more on the use of web-based technology such as HTML, JavaScript, Ajax, PHP, and so on and so forth. An M2M area network comprises of machines which have embedded hardware modules for sensing, actuation, and communication. Various communication protocols can be used for M2M local area networks, which could be Bluetooth, Modbus, MBus, wireless, MBus, power line communication, 6LoWPAN, IEEE 802.15.4, etc. The communication network provides connectivity to remote M2M area networks. The communication network can use either wired or wireless networks, IP-based, while the M2M area networks use either proprietary or non-IP based communication protocols. The communication network used IP based networks. M2M gateway. Since non-IP based protocols are used within M2M area networks, the M2M nodes within one network cannot communicate with nodes in an external network. So to enable the communication between remote M2M area networks, M2M gateways are used. These are the differences between IoT and M2M. Sensor is a device used for the conversion of physical events or characteristics into the electrical signals. This is a hardware device that takes the input from the environment and gives to the system by converting it. So we have already understood the basic of Internet of Things. Now let us try to understand that what are the essential building blocks of Internet of Things. So one of the very essential components of Internet of Things is sensors, and the other one is actuators. Whereas the sensors basically sense the physical phenomena that are occurring around them, um, and the actuators basically based on the sensory information. The actuators, they actuate, that means they perform some actions on the physical environment. So they take some actions based on what has been sensed. So essentially, if we see that we have a gradual phase-wise approach to building Internet of Things, so we have sensors which are sensing the sensors. They sense different parameters depending on the sensor being used. For example, temperature, pressure, humidity conditions, lighting conditions, and so on. Then what will happen is these sensory information are going to be sent over a connected system. That means over a network, that information will be passed and also involve cloud and so on. And finally, that information is going to be transmitted based on what has been sensed, and based on the requirements, some physical action is going to be taken by any actuator. So maybe a bulb might be turned on if certain conditions in an agriculture field has happened. Maybe if the field, based on the sensor, it is found that in an agriculture field, the field has run out of stagnant water that is required for paddy crops. Then what might be required is based on based on that sensory information. Automatically, the valve of the water pump, the deep to well that is used, or a shallow tube well that is used for irrigation, automatically that valve will be turned on so that the field gets irrigated, so that can be done to the process of actuation. So we have sensing, we have IoT, or simply the network, and then we have this actuation. So sensing, network, actuation, we start with the sensing component. Now we will try to understand how actuation is done. So when we talk about sensing, we need to understand what is sensing. So basically, a sensor, it detects or senses the change in the ambient conditions, or it can also sense the state of another device. So maybe one sensor can check and sense how and what is the state of another device. So that is what is done with the help of sensing. So some physical property of the ambient conditions of the environment in which the sensor is in, or of another machine of, or a system, a separate one, these can be sensed with the help of sensors. So the sensors based on certain stimuli, the different stimuli might be there. They can measure the thing in the physical characteristics of the environment of the system and so on. And these changes are basically converted to electrical signals. For example, for a heat sensor, this heat is converted to electrical signals, and this is for temperature sensors. And for temperature sensors, the heat is converted to electrical signals, and for sensors such as atmospheric pressure sensor, the atmospheric pressure is basically converted to electrical signals. So we have different sensors which measure different things, but then these sensed values are converted to respective electrical signals. Now there is an associated terminology which is for the transducers. The term transducers basically convert one form of energy into another form of energy, being converted into another. For example, in a microphone that we have in a microphone, so the sound waves are converted to electrical signals, and then to a output device like a loudspeaker, and we are able to hear the sound. This is an example of a transducer. So these term sensors and transducers are very common. They have a lot of overlap, and we have to understand the distinction between these two. There is a lot of misunderstanding. People conceive sensors and transducers. We use these terms almost interchangeably, but these are different. There are differences. So the word transducer is a collective term which includes sensors as well as the actuators that I was telling you. Before the sensors can sense what is going on around them and convert it to electrical signals, etc. And the actuators can basically perform these actions by maybe switching voltages or currents. Sensors have different features. They are sensitive to the property, the physical property that is being measured. They are sensitive only to that measured property. So basically, a temperature sensor can sense only the ambient temperature of the room, and it is insensitive to other changes, maybe changes in the atmospheric pressure or changes in the lighting condition of the. There is a terminology which is called the resolution. The resolution of a sensor is basically defined as the smallest change that it can detect in the quantity that is being measured. So the smallest change that it can detect, the resolution of a sensor with a digital output is usually the smallest resolution of the digital output it is capable of processing. So based on the output, the sensors can be classified as analog or digital, and based on the data type, they can be classified as scalar or vector sensors. So in the analog sensor, what we have these sensors in continuous analog output. So for example, tint temperature sensor continuously changes in the temperature are going to be measured, and the output is going to be an analog signal. Digital sensors basically gives digital outputs on and off. For example, discrete digital values are given as outputs by these digital sensors. Then scalar sensors basically measure scalar variables which can measure only the changes in the magnitude, whereas the vector sensors not only the magnitude but also the direction. So scalar sensor would be temperature sensor is an example of scalar sensor because irrespective of which orientation you put the sensor temperature sensor or in which the direction you are taking it, it is going to give you the magnitude only the changes in the magnitude of the temperature. On the contrary, we have the vector sensor. For example, the camera sensor or the accelerometer sensor whose values are dependent on the orientation, on the direction, and so on. Direction in which the sensor is being put and the weight is measuring. So it is dependent on that. We have analog sensors, we have digital sensors, we have scalar sensors, and we have vector sensors. So analog sensor, I have already mentioned about analog sensors, temperature sensor. Temperature is typically measured with the help of thermocouple. Thermometers are quite common. But thermocouple is something that is used in the geysers. For example, you have two different metallic strips, for instance, and these strips they can bend and so on. So these based on the amount of bending, etc. They measure the changes in the temperature. So if you calibrate the thermocouple, accordingly it is going to give how much temperature has changed, and depending on that, one can understand how much the liquid has heated up or has cooled up. Digital sensors produce digital discrete voltage levels or signal levels. So binary values like 0 and 1 are on and off are output the digital sensors. Scalar sensors measure only the magnitude, physical quantities such as temperature, color, pressure, strain, etc. These are scalar quantities, and measurement of the change of magnitude is sufficient to convey the information. On the other hand, vector sensors produce output signal of the voltage, which is generally proportional to the magnitude as well as the direction and orientation of the quantity that is being measured. So, physical quantities such as the sound, image, velocity, acceleration, orientation, these are all vector quantities, and their measurement is not just dependent on the magnitude but also on the direction. So, for example, accelerometer sensor, they give outputs in three dimensions: x, y, z, and coordinate axis. Next, actuation. Actuation is a device that converts the electrical signals into the physical events or characteristics. It takes the input from the system and gives output to the environment. For example, motors and heaters are some of the commonly used actuators. So based on the readings of the sensor, we have already seen different types of sensors in the previous discussion. And based on the readings of these different types of sensors, some action might be required to be taken, and that is done by actuators. These actuators basically perform certain actions on the environment, on another system, on a device, and so on. There are different examples of actuators. They can have principle of principle working principles which are based on electronics, then electrical, mechanical systems, and so on. So they basically use some kind of control behavior, some control signals are sent. So this is how these actuators they perform. An actuator is a component of a machine or a system that moves or controls the mechanism of the system. So typically, these actuators are based on some control system, and these control systems act on the environment. So an actuator basically requires some kind of a control signal and a source of energy for their functioning. So typically, I said that control signals are required for the actuators. So when these actuators receive a control signal, they respond by converting that energy into mechanical motion. So mechanically, something is going to be done. This is an example. They convert that electrical signal, some control signal, into mechanical motion, and that control signal can be simple, which can be based on some mechanical or electronic system, or it can be software based like a printer, driver, robot control system, a human, or any other input. So what we have are uh, three types of actuators. One is these electric based actuators, we have these pressure based actuators, and we have these mechanical based actuators. Each of these each of these they send control signals, and based on that the actuation is going to be performed. Next, what are the IoT components we have? When we talk about IoT, we have these different things which, as I said in one of the uh, discussion in one of the previous discussions, these are basically physical objects once again. So these physical objects are fitted with the different sensors, and these sensors basically sense different physical phenomena that are occurring around them. So these sensor fitted things, sensor actuators, and different other embedded devices, these are one component of the IoT. But these become different nodes in the network. These are the individual nodes in the network. So then what we have is these nodes, they have to communicate with one another, and the information that is sensed by one of these sensors fitted to these nodes, this information from the sensor and the other sensors are taken and are sent to other sensor nodes, the destination nodes. So uh, first this information has to flow through local network, and then if the destination is outside this local network, then it is sent through the internet. Typically, if you are talking about an IoT, which is basically internet based IoT, then basically it is going to flow through the internet or some other wide area network, and finally it is going to arrive at the intended destination node. And maybe there can be some, at that point actually there can be some analytical engine which is running on some backend server. Those could be there, and from that point, from that decision, from these analytics, they can run on these servers. Decisions about actuation could be made. So what we see is from sensors to actuators through the local area network, the internet involving, backend services, analytics, which includes again high-end processing at different servers and different complex algorithms, execution of different algorithms which are based on maybe machine learning neural networks and so on and so forth. These are all required. Basically, what happens is we can conceive an IoT as a very complex system involving sensors, actuators, networks, local area, wide area internet, and different servers, different algorithms, machine learning, and so on, all executing together to make the system function as one single entity. So going back, we have in this local network, as you are saying, then we have the internet, we have the backend services, and finally the applications that I have been served. So these are the different components of IoT. So this is the scenario that I was referring to earlier. So what we have, we are these different things. These things could be like different physical objects which are fitted with different sensors. These things could be telephones, lightning systems, could be cameras, could be different other scanners, sensors like the temperature sensor and so on. And these things are able to communicate with one another with the help of wireless technologies like Zigbee, Bluetooth, Wi-Fi, and so on. So as you can see that this wireless basically helps these different devices to talk to one another, and this information from these devices they will go through local network, and from a local network they will go through the internet to these data are basically sent to the backend services involving different servers, processors, and so on and so forth. For running different analytics, and then based on that, different devices can be actuated, maybe a pump. This is an example that I gave earlier in a previous discussion, basically for agricultural purposes. The use of IoT pump might be actuated based on the data that is received from the sensor nodes and based on analytics are run at the different servers that are involved in the backend service processing. So in terms of the functional components of IoT, one of the very important things is basically interaction. Interaction not only with the physical environment by these different sensors, but also interaction and communication with the different devices. That means the different nodes in the IoT network, then comes the processing. So processing and analysis of the different functioning and the operations that can taken place. So processing of the data, the processing of our operations. So this is another component. The third functional component is basically the interaction, typically with the internet, and because of at present most of the time the most of the IoT implementations are still using the internet. So it is all internet powered IoT implementations. So internet interaction is one of the very important components of building IoT. And then we have the web services, machine to machine communication, and so on. So basically, what is going to happen earlier? Most when you talk about web technology, typically we are talking about human to machine communication. Web service we are talking about some machine sending or some equipment basically sending that data to another machine for further processing or machine to machine communication is involved and offering different services. So one machine offers some services to another machine and so on. So this is basically, this sort of thing in a IoT scenario is taken care of typically. And then we have the integration of different applications, services, and the user interface to access the IoT. That is another component. So there has to be a user interface, a human interface to access the IoT network or the IoT, mega network. So looking at this particular figure, I would try to clarify how IoT implementation is typically done, and it can be done to achieve different application needs. So this is a figure which shows that we have different sensors, processors, and radio. It refitted to each of these devices or the sensor nodes or the sensor modes or the IoT modes as you may want to call them. So these modes they talk to one another, but these different sensor nodes they are basically within the jurisdiction or the domain of the gateway. So the gateway is basically tasked to assign different locally unique addresses to these different nodes, to these different IoT nodes, and the gateway basically takes care of the local addressing within that particular local area network. So from that point, all the data can flow through a proxy server if internet access is required. So it will go through the internet, then a WebSocket, and then from WebSocket, it goes through a cloud server. That means where a lot of analytics and backend processing takes place, and based on that actuation, based on the analytics and the infer, and says that and run from the sensor data activation of different devices can takes place. For example, lightning a particular lamp. For example, lighting a particular lamp could be the actuation of the particular lamp. We have different interdependencies that are evolved in the implementation of IoT. So if we look at IoT from another perspective, or we have sensors, we have actuators, and a bunch of other things that they are in between as shown in this figure. So this is basically the entire span of these different embedded devices. Networking types, we have wired and wireless. Early networks before 2008 were mostly wired. Most networks nowadays, however, will use a combination of wired and wireless networks. Ethernet is the data link protocol used in wired networks. This is unlikely to alter with the Internet of Things, as most IoT devices will be wireless. The following are the benefits and drawbacks of wired networks. Almost all laptops, PCs, and netbooks, even ones as old as 80 years, include Ethernet connectors. Wireless networks are slower than wired networks. Data rates were boosted from 10 megabits per second to 1 gigabit per second on a regular basis. The majority of residential networks use speeds of 10 to 100 Mbps. Wireless is less secure. Disadvantage of wired networks: you need to use cable, which is unattractive, difficult to install, and costly. It is difficult to utilize between buildings. Many of these drawbacks are overcome by a new technique that uses mains cable on home and email and home and small office networks. Offline networking is common. Mobile phones and tablets are not supported by wide networks. Wi-Fi is the data communication protocol used by wireless networks. Other wireless options for the IoT, on the other hand, are being developed. Wireless networking technologies for IoT can be found here. The following are the benefits and drawbacks of wireless networks. In general, they are easier to set up. It operates on both private and public networks. There are no cables necessary. Mobile phones and tablets are supported. Generally, networks that are wireless are slower than those that are wide. Range is a limitation. Eavesdropping is possible. Depending on the setup, it may not be as secure. Network topology, there are a variety of methods for connecting network nodes. This is not usually consideration in small networks, but it becomes increasingly significant as networks grow larger. There are variety of methods for connecting network nodes. Wi-Fi, Bluetooth, and other common connection technologies are intended to work with a specific network layer. Understanding these topologies is crucial for constructing networks and selecting connection protocols. Common are bus, ring, mesh, star, hybrid. Early Ethernet networks, modern Ethernet networks, and Wi-Fi networks all used a bus structure, use a hybrid star bus structure. Wi-Fi and Bluetooth, on the other hand, are being improved to accommodate mesh networking. Personal area network is a network that connects local devices such as a computer to a printer. LAN, local area network, connect devices in a single or multiple offices. Metropolitan area network is a network that connects devices across numerous buildings such as a campus. Differences between M2M and IoT. Under M2M, proprietary or non-IP based, IoT IP based, M2M homogeneous, IoT physical objects that have unique identifiers, M2M more on hardware, IoT more on software, M2M collected in point solutions and often in on-premises storage, IoT collected in the cloud, can be public, private, or hybrid cloud. M2M applications are diagnosis applications, service management applications, and on-premises enterprise applications. IoT applications are analytics applications, enterprise applications, remote diagnosis and management applications, etc. So we have different core layers, and as the name suggests, sensing layer basically takes care of sensing through different RFID tags, sensors, and so on and so forth. And then data are sensed, are acquired, and so on, are sent to the next layer higher up, which is the network layer. The network layer basically serves sensor networks, social networks, different other networks and databases, internet, and so on. That is the network layer. Then what we have? We have the service layer, which deals mostly with the service delivery, such as service, division service, integration service, repository service, logic by business, and so on. So all these different things that I involved with the offering of the services to support the business functions. Then we have the interface layer, we have the application front end, we have a contract interface and application APIs. So this becomes the interface layer, and then we have the security issues, which basically span all these different horizontals. So in terms of the categorization of IoT, it can be categorized into two. One is the consumer IoT, which is what typically most of the people tend to use, and these are here. Basically, these different devices they communicate with another through these local networks, and it can be find a further communication can also take place over the internet as well, depending on the requirements, either local or through the internet. Then we have the local communication, which is typically done via Bluetooth, Zigbee, or Wi-Fi. So basically, this local communication is constrained within the bounds or within the domain of the IoT gateway. So this is the consumer IoT. Then we have the industrial IoT, which is basically quite similar to the consumer IoT, but the application interest is in the industrial sector. So we are talking about manufacturing industries with different machines. With these machines are fitted with different IoT devices, and they together become the IoT device. They have different sensors and so on. Feature are there which can node as a whole can communicate with other machines and so on. So this becomes the industrial IoT, and basically there are different communication that takes place between the different nodes as well as different industry specific technologies. So we have seen M2M gateways. Likewise, we have IoT gateways also. So this is what I told you, that in a local network we have this locally unique addresses, and that is there within that local area network, IoT network. So these local addresses basically they take care of the addressing of the different nodes. So what are these gateways doing? So the gateways basically take care of the addressing, but then in this is what the gateway structure looks like. So this is what is here. So we have the local network on one side of the gateway. So we have the global network on the other side of the gateway, and this is where the gateway. This is how the gateway looks like. So the gateway has functions, different tasks such as switching, routing, protocol conversion, firewall, and VPN services, security as a whole, and processing. So this is what a gateway does, and the gateway with the local network and the global network communicate via the wider wireless channels and so on. This is how the IoT gateways function. Different associated technologies of IoT involving big data, cloud, smart grid, Internet of Vehicles. That means different vehicles on the road are fitted with different IoT devices which can communicate with one another, and different intelligence about the route traffic conditions, about the offering different roadside services can make possible with the help of Internet of Vehicles. Then we have the machine to machine communication where one machine turns to another without any human intervention. We have telemedicine offering offering healthcare services to the remote hospitals, remote healthcare centers, and so on. Cyber physical systems, we have 3G, 4G, 5G, we have SDN, and so on. SDN, software defined networks. So these are the different associated technologies which together make IoT to deliver IoT solutions. Now, if you try to make a side by side comparison between the IoT stack and web stack, different layers, communication layers, and application layers that communicate, uh, layers remaining the same between IoT and web. But what is different is what we have a new set of protocols that are used over here. So the new set of protocols, and additionally in IoT, unlike in the case of web things such as different types of management of the network, management of the power, management of different other resources, these are all additionally taken care of in the IoT node in the IoT stack, which is not available in the case of web. And this is very much required because in the case of IoT, we are talking about heavily resource constrained nodes, and these heavily resource constrained nodes basically require network management in terms of energy, in terms of processing, in terms of data, and so on. So forth. There are different key technologies that basically helps IoT survive. We have the future internet knowledge aggregation open through data assignation, data collection, processing, and analysis. Then we have different standards. We have sensor networks, we have communication, we have cloud computing, we have discovery services, nano electronics, embedded systems, software system integration, and last but not the least, what is this over here on top is the security and privacy issues. So security and privacy issues are paramount in IoT because there are heavy concerns because we are dealing with resource constraint nodes, with communication constraints, bandwidth constraints, processing constraints, energy constraints, and so on. So these nodes become very much available to different types of attacks, different types of security breaches, and also because IoT systems are very much detailed, intensive. There is a lot of information that flows in through the network as a consequence of which the privacy of the individuals or the organizations might be at stake. So security and privacy and trust also, which is not mentioned over here, these are very much important to cover IoT technologies. There are different types of challenges: security, scalability, energy efficiency, bandwidth management, interfacing, interoperability, interoperability. So when we are talking about interfacing, it is typically we are referring to device interfacing. So different, one device talking to another device, maybe these devices do not belong to the same vendor. They are not running the same stack. They are not following the same standard and so on. So then consequently the interoperability issue. How to make these devices talk to one another? How different protocols, the different devices, the different algorithms are going to handshake with one another. So this is another challenge which is typically of IoT implementations, and then we have data storage and analytics and complexity management with tools such as SDN. So SDN basically helps in addressing the complexity of systems by decoupling the control plane from the detect plane of the networks, different considerations, and they are for building IoT. One is that we have a straight network architecture which can be used by different IoT implementations. The different wireless networks are used issues such as traffic management, load management, then variations in the different wireless network forms. For example, wireless personal area network, W tons versus wireless body area network interoperability, which I have already mentioned just a while back. Then network management and overlay network. So basically, the overlay network takes care of some kind of a virtualization of the physical devices, and one type of these physical virtual devices and the networks and the overlay is created. This is basically the overlay network. Scalability is involving flexibility within the internet, then integration of different IoT devices. They are manufactured using different standards, maybe in using different, vendor specific protocols. So IoT integration is a very complex issue, which basically dictates the scalability of the system. Large scale deployment issues and real time connectivity of billions and trillions of devices. With this, um, we are going to cover uh, many other issues involving the networking aspects of IoT in the subsequent lectures, and from there we can understand from the subsequent lectures we can understand how farming an IoT is very complex. What are the different protocols that are how they are may not be a single isolated or a single thread head. Let us say one protocol for IoT as a whole, but there are all these individual protocols ideally here. So how that can be taken care of, or how can architecture be sent up between these different IoT devices manufactured by different vendors. So like this actually there are different complexities that I have involved. So we have really talked about that in the subsequent quadrants. So with this, I'm going to end this session. Thank you, one and all.